Question 11d. By expressing the square root of 3 sine x plus 3 cos x in the form a sine x plus alpha, solve the square root of 3 sine x plus 3 cos x equals the square root of 3 in the interval x greater than or equal to 0 and less than or equal to 2 pi. The first step is to find the values of a and alpha in the identity a sine x plus alpha is identical to the square root of 3 sine x plus 3 cos x. Expanding the left-hand side, since we have the sine of a compound angle, we have a outside of sine x cos alpha plus sine alpha cos x is identical to the square root of 3 sine x plus 3 cos x. Expanding the left-hand side further and switching the sine x and the cos alpha around, we have a cos alpha sine x plus a sine alpha cos x is identical to the square root of 3 sine x plus 3 cos x. So I just wanted the terms involving alpha to be written first. Now, equating the coefficients of sine x and cos x, we have a cos alpha is equal to the square root of 3, and a sine alpha is equal to 3, since a cos alpha is the coefficient of sine x, and that should equal the coefficient of sine x on the right-hand side, which is the square root of 3. And likewise for the coefficient of cos x. So we can write that as two equations. A cos of alpha is equal to the square root of 3, and we'll call that equation number 1. And a sine of alpha is equal to 3, and we'll call that equation number 2. Now, to find the value of a, we square both equations and add them together. So equation 1 squared plus equation number 2 squared. So we have a squared cos squared alpha plus a squared sine squared alpha is equal to the square root of 3 all squared plus 3 squared. Factorising a squared, on the left-hand side, we have a squared outside of cos squared alpha plus sine squared alpha is equal to 12. And we have a Pythagorean identity here, and that's equal to 1. Hence, a squared is equal to 12. I'm taking the square root of both sides when we're only interested in the positive square root. A is equal to 2 square root of 3. And we'll call that number 3 there. Now, to find the value of the auxiliary angle alpha, we take equation number 2 and divide it by equation number 1, because that'll cancel out the a, and we end up with a term involving tan of alpha. So a sine of alpha over a cos of alpha is equal to 3 over the square root of 3, and the a's cancel, and we end up with tan of alpha is equal to the square root of 3. And taking the inverse tan of both sides, we have alpha is equal to 60 degrees, or pi over 3 radians, but we're working in radians, so pi over 3 is the value of alpha. Now to solve the equation, a sine of x plus alpha is equal to the square root of 3. Now that we have the values of a and alpha. So a is equal to 2 root 3 and alpha is equal to pi over 3. So substituting those two values for a and alpha, we have 2 square root of 3 sine of x plus pi over 3 is equal to the square root of 3. So now we just solve for x. Dividing both sides by 2 root 3, we have sine of x plus pi over 3 is equal to half. X plus pi over 3 is equal to the inverse sine of half, and inverse sine of half is pi over 6, or 30 degrees, but we work in radians in this question. So that means that x plus pi over 3 is equal to pi over 6, 5 pi over 6, 13 pi over 6, and so on. And this gives rise to two cases, since we're only working in the interval x greater than or equal to 0 or less than or equal to 2 pi. So pi over 3 needs to be subtracted from these values such that the value of x needs to be in the interval that I just stated. So case 1, we can take 5 pi over 6 and we subtract pi over 3 from that to make x the subject of the formula, and we get the value of x equal to pi over 2. And case number 2, x is equal to 13 pi over 6 minus pi over 3, and x equals 11 pi over 6. So therefore, the solution is x equals pi over 2 or 11 pi over 6 radians.